Let's dive into the world of stochastic processes. A stochastic process is essentially a collection of random variables that are indexed by time. Imagine it as a way to model systems that change randomly as time passes. You can think of it as a family of random variables, each representing the state of a system at a particular moment. The formula here represents the set of random variables x of t, where t belongs to the set t. This is how we mathematically denote a stochastic process, a fundamental concept for understanding systems that evolve in unpredictable ways. Now let's explore random walks, which are a type of stochastic process. A random walk describes a path that consists of a series of random steps. Imagine a person walking around aimlessly. Each step they take is random in direction and length. This is essentially what a random walk models. Mathematically, we can represent a random walk as x subscript n equals delta 1 plus delta 2 plus, and so on up to delta n, where each delta subscript I represents an independent random step. This means that each step is not influenced by the previous steps, making the walk truly random. Let's discuss the mathematical framework behind a simple random walk. A simple random walk can be mathematically represented as s subscript n equals z subscript 1 plus z subscript 2 plus, and so on until z subscript n. Here, each z subscript I can take on a value of -1 or +1 with equal probability, that is 1 by 2. This means that at each step, there's an equal chance of moving one unit in either the positive or negative direction. Some key properties of this simple random walk are: the expected value of s subscript n, which is written as e of s subscript n, is 0. This means that, on average, the walk will end up at its starting point. And the variance of a subscript n, written as var of a subscript n, is equal to n, the number of steps taken. This indicates how spread out the possible locations are after n steps. Let's see how random walks are used in finance, particularly in stock price modeling. Stock prices are often modeled using a geometric random walk. This assumes that price changes are unpredictable. The formula here describes this geometric random walk. S subscript t plus 1 equals S subscript t, multiplied by e raised to the power of mu plus sigma times z subscript t. In this formula, S subscript t plus 1 represents the stock price at time t plus 1, S subscript t is the stock price at time t, mu represents the expected return, sigma represents the volatility or standard deviation of returns, and z subscript t is a random variable that follows a standard normal distribution. This model suggests that stock prices evolve randomly over time, with changes depending on both a constant growth rate and a random component. Now let's explore the applications of random walks in biology, focusing on molecular movement. Brownian motion is a key concept here. It describes the random movement of particles in fluid environments. Think of tiny particles jiggling around in water, bumping into each other randomly. Examples of this include DNA diffusion, protein folding, and genetic drift, all of which follow random walk patterns. This means that the movement of molecules and genes can be modeled as a series of random steps, providing insights into various biological processes. Let's examine the use of random walks in physics, specifically in diffusion processes. The Einstein relation connects random walks to diffusion and Brownian motion, linking microscopic random movements to macroscopic diffusion phenomena. The formula here represents this relationship. D equals the limit as t approaches infinity of the average of x squared of t, divided by 2t. In this formula, d represents the diffusion coefficient, which measures how quickly particles spread out. X squared of t is the mean squared displacement of a particle at time t, representing how far it has moved from its starting point on average. This equation shows how the diffusion coefficient is related to the average displacement of particles over time, demonstrating the connection between random walks and diffusion processes. Let's move on to Markov chains. A Markov chain is a stochastic process where future states depend only on the current state and not on the past. Imagine a game where the next move depends only on where you are now, not on how you got there. This is a Markov chain. The memoryless property of Markov chains can be expressed as the probability of x subscript n plus 1, given x subscript 0, x subscript 1, up to x subscript n equals the probability of x subscript n plus 1, given x subscript n. This means that the probability of the next state, x subscript n plus 1, depends only on the current state, x subscript n, and not on any of the previous states. Let's explore the mathematical framework of Markov chains, specifically the transition matrix. State transitions in a Markov chain are described by a probability matrix P. This matrix shows the probabilities of moving from one state to another in a single step. The formula here describes the elements of this matrix. P subscript ij equals the probability of x subscript n plus 1 equals j, given x subscript n equals I. Here, P subscript ij represents the probability of transitioning from state I to state j in one step. The condition means that we are calculating the probability of being in state j at time n plus 1, given that we are in state I at time n. Let's look at how Markov chains are used in finance, specifically in credit risk modeling. Credit ratings, such as those assigned by agencies like Standard & Poor's or Moody's, can be modeled as transitioning between states following Markovian dynamics. This means that a company's credit rating can change over time, and the probability of moving to a different rating depends only on its current rating. An example of this is that credit ratings may transition from AAA to AA, then to A, then to BBB, and eventually to default states modeling credit deterioration. This allows financial institutions to assess and manage the risk associated with lending to different entities. Let's investigate the applications of Markov chains in biology, particularly in population dynamics. Gene frequency changes in populations can be modeled as following Markovian evolution. This means that the frequency of a particular gene in a population changes over time, and the probability of the next frequency depends only on the current frequency. Birth-death processes, which model species survival and mutation patterns, are examples of this. These processes can be analyzed using Markov chains to understand how populations evolve and adapt over time. Now, let's examine the use of Markov chains in physics, specifically in statistical mechanics. Monte Carlo methods use Markov chains to simulate complex physical systems. These methods involve generating a sequence of random states, where each state depends only on the previous one, and then using these states to estimate properties of the system. Thermal equilibrium and phase transitions can be modeled through these state transitions, allowing physicists to study phenomena that are difficult to analyze through traditional methods. These simulations provide valuable insights into the behavior of physical systems. In summary, both random walks and Markov chains provide powerful tools for modeling uncertainty across various disciplines. Random walks are useful for modeling systems with independent, random steps, while Markov chains are ideal for systems where the future depends only on the present. From stock prices to protein folding, stochastic processes capture randomness in nature, providing valuable insights and predictions in various fields. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.